Welcome to this course in Statistical Problems and Simulation. This is the first course for Ph.D. students in telecommunications and networking. This is the first of 5 lectures. In this lecture we will cover introducing the concept of statistical simulation, and we will also look at modeling in communications and telecommunication systems in general. I'm presenting this slide set will be Jens Sander. I'm a professor in radio communication systems at the Communication Systems Department at the School of ICT at KTH in Stockholm. The course has several objectives. The main objective is to provide the fundamentals of experimental design techniques in stochastic simulation, and the focus is on telecommunication systems and networks. After the completion of the course, the idea is that the students should be able to generate random variables, arbitrary distributions. They should be able to make parameter estimates based on simulation results and to assess the statistical errors of their simulation studies. Further, the student should be able to test hypotheses with simulations. The student should be able to design simulations to lower the variance of usual simulation estimators in order to make the simulations more effective. And finally, the student should be able to determine whether the stochastic model chosen in their simulation is consistent with the set of actual data that they have. The course will be based on the course book by Sheldon Ross, Simulation. We're going to use the 5th edition. This is available on Amazon, and it's published by Academic Press. Earlier editions than the 5th edition can also be used, and we will provide translation tables for homework problems. I can also recommend the additional reading book. This is the older book by Brian Ripley, Stochastic Simulation from Wiley from 1987. And that book deepens the understanding of how to generate random numbers and the statistical problems of random number generation and validation. And also goes a little bit deeper into time series analysis when we want to analyze large systems and their transient behavior. How to use this video? Well, first of all, I would like to say that the video complements the textbook and highlights important parts of the textbook material. And the videos do not replace the textbook at all. There are a number of quizzes in the forms of multiple choice questions, and a few simple problems are included. My recommendation is that you pause the video and make really serious attempt to answer the questions and try to solve the problems before continuing viewing. Let me give you an examples of the quizzes here. This is a multiple choice quiz. 4 statements, and we recommend that you pause the video here and look at the 4 statements, and then you try to determine which of them are correct. Several answers may be correct, so I give you a few seconds here to ponder on the questions and which of the alternatives A, B, C, and D may be correct. And then we continue. And here are the answers to the test quiz. Options B and C were correct. The quizzes are there to help the students to diagnose their skills in the subject, and it is important that you've understood the questions and the answers before continuing in the lecture. If it's so that you have missed some of the questions or didn't get the answers right, I think it's a good idea to go back and review the previous part of the lecture to make sure that you have the complete understanding. So now let us go to the first section here, where we're going to discuss models and the use in engineering sciences. Before we go into models, let's look a little bit about what types of research Research comes in a number of flavors, depending on the complexity and the detail that we study reality. You can say that we can start with exploratory research. We go into a new field, nothing is known, we just need to explore what's going on. As we know more and more, we get into descriptive phase. We categorize and catalog different events and phenomena that go on this world. And then we continue into explanatory research, where we try to explain why things happen, what causes different events to happen, and what causes different phenomena. And finally, normative research, that's sort of the engineering domain. How can we improve on reality? How can we make things better for humanity in this reality? You can say that going down the list requires an increased understanding of what's going on in the world. You can say that the three first types of research are so-called ex post facto research, meaning that that is research built on observations. There's a reality that you actually can observe, whereas in the normative domain, the engineering domain, normally we operate in a hypothetical world. We want to build a bridge over the gorge, but the bridge isn't there yet, so we have to study the hypothetical bridge and try to design it in order to make it withstand the forces of nature and weather and wind and things like that. An important concept in research, and particularly engineering research, is modeling. We have a complex reality. It's a complex system. Examples can be the solar system, the planets and the sun, the weather, the climate system around the Earth, or even the rush hour traffic situation in a major city. And what we like to do is to build simplifying descriptions of this complex reality. And we do this by removing what we hope are irrelevant items for those mechanisms that we're really interested to study. And the models can then be used to describe reality. They can be used to understand or analyze reality. And finally, what is then important, in particular for engineering, is that models can also be used to predict things in the future, or predict things, answer what if type questions. A very good example of this is Newton's gravity model that helped us to explain the motions of the planet, and for instance to predict solar eclipses and even to predict the existence of planets that to that point were unknown. Let's discuss how engineers and natural science use models. The predominant approach to modeling is the hypothetic deductive approach. And this means basically that we ad hoc come up with a model, or maybe may call it a theory or hypothesis, and to describe reality. And from this model we deduce certain events or predict certain events or behavior. The events and behavior are compared with reality, and if the events and reality checks out, then the model is strengthened. If the events that we predict and reality do not check out, the model is falsified. It has to be discarded or modified, and we repeat the process. A model is said to be become stronger and stronger the more clever attempts to falsify it withstands. Let's review a few of the model types that we see. A very common model that we see for complex systems is what we call a mechanistic model. We have a complex system containing a lot of different items and different particles or components. And all these components, they follow simple rules. And so even though the rules are very simple, they form a very complex system with maybe very difficult to predict behavior. But still, we understand the individual components, how they operate. On the contrary, we can use a instrumental model. Here, the reality is so complex, it becomes very difficult for us to describe them. Even though, for instance, in this gas container with all these molecules, even though in principle it would be possible to describe all the molecules and their individual motions, it is simply impractical due to the sheer numbers of the molecules. So instead, we use an instrumental model, the gas law on the right-hand side, which describes the relationship between the pressure and volume in a gas and the temperature. You can say that the instrumental model on the right-hand side, it cannot understand why and how things work in detail, but it still be very good in describing the behavior or even predict the relationship between the PV and T in this very, very complex system. Let's discuss some of the properties of models and what requirements we can put on models. Let's look at this example where we have plotted the observation y as a function of parameter x. There are different aspects on modeling. We can propose a model to describe the behavior of y as a function of x. And if we want to make simplicity as premium, we may explain y as function of x as a straight line like this. This is a 1 or 2 parameter model. You can see that the accuracy will be somewhat compromised, but it still seems like a pretty good description of the values. The alternative approach is to go for accuracy. And so we can fit a much more complex. This may be a 8-parameter curve that you will fit to the data points, and the fit, of course, will be much more accurate. The error between the red curve and then the dots is much less prominent. So we can see there is a compromise between simplicity and accuracy. This has been studied in history of science over many years, over more than 1,000 years actually. And maybe the most famous quote here from in history is the one of William of Ockham, usually called Ockham's razor, and the saying that we among 2 explanations of the same phenomenon, we prefer the simplest explanation. So if we have 2 models that give roughly the same accuracy, we should choose the one with the fewest parameters, would be the corresponding lesson that we would learn from our example. So what are our stochastic models? Well, stochastic models are models for systems that are very complex, where there are very complex interactions, and where we can find no closed form models or simple models that explain the behavior of the system. Stochastic, or we can call them probability-based models, they are instrumental models. They do not describe the details of the systems, but use aggregate descriptions. And it is usually used to describe the non-explainable components that are so complex that they cannot be simply described. They can be used in combination with mechanical components as well. So some of the phenomena that we exactly know how they work, we can describe with mechanical components, but then we add stochastic or probabilistic components for those that we cannot describe. The drawback of these modeling is that we cannot no longer get exact results, but the descriptions or the output data that we can get from using these models are described in statistical terms. We can get averages, distributions, standard deviations, correlations, and similar. Examples of situations where stochastic modeling can be appropriate is complex systems like the traffic behavior in rush hour in a big city, the behavior of the molecules of a gas in a container, very large number of components, very large number of molecules, Or the packet traffic in the internet is another good example of very complex systems where probabilistic models can be appropriate. Yeah, a final reflection on engineering science approach. As we mentioned before, normative research is normally dealing with hypothetical reality and not observable reality. So, and in fact, when we take the example that we want to build a bridge, we have a reality. We have the gorge, we have the soil, we have the mountains around where we want to build the road and the bridge. But the bridge itself is at the design phase still a hypothetical system that we have to model. So we want to model both the reality and the hypothetical system in it. And based on this model, we design. We use the design to get the performance. Will the bridge withstand the load of the traffic and then the weather conditions? And then we verify the model by actually building the bridge, and hopefully the bridge will stand. So the engineering cycle is to propose hypothetical systems, model the behavior of reality, and now which is then reality plus the hypothetical system, and we want to design or optimize the systems for the required performance, and we verify by building the system. Sometimes, however, building the system itself can be very expensive. Building the internet or building a very expensive bridge can be very costly, and we cannot afford failure. So we really need to see if we can verify our systems without actually building the system. A common approach is to then really rely on the model and say that, okay, the model is correct, and we make a design, and based on the design we analyze the performance of the bridge, and we say this is the bridge will hold. This is of course not doing the verification at all. A better approach in this case is to use a layered model. We use a simple design model to actually do design and to estimate the performance. The design model is highly simplified, and which makes it easy to compute the performance, and we can quickly do very many design cycles and to check the performance of our system. But then instead of building the bridge, we expose our design to a verification model, a much more complex model that takes more features into account, and but on the other hand takes longer time to compute. And we verify this model by using this model, and after we're satisfied with the design, then we actually build the bridge. Typically design models are simple analytical models, mathematical models, and the verification model could be a complex stochastic model for which stochastic simulation could be a viable approach. So here comes quiz number 1 on modeling and scientific methods. Again, pause the recording at this point and try to figure out the correct answers. Again, several answers may be correct, and I give you a few seconds to ponder about the correct answers. And when you finish, you can move on to the answers. Correct answers are B. Modeling and engineering is mostly about hypothetical situations that still not exist. And D. Among two models with the same accuracy, one should choose the simplest, the one that uses the fewest parameters. So let us now go to simulation and stochastic modeling concepts. Let's start out with a definition of simulation. We define simulation as empirical experiments with a mathematical model of our system. And you can see this in the following way, that we have our system, which is sort of a mathematical model actually of our complex system. And this mathematical model is driven by input data or stimuli from the left-hand side. And it will produce output, and it could be events or performance-related measures. And the system model may have an internal state, and we may or may not observe the state. And the output is a function of the stimuli and the state, and this function f is determined by the system. And also the state progression is also a function of the stimuli and the previous states. So based on this very general description of system modeling, we can now define a number of simulation techniques based on the model type or the stimuli type. When the stimuli or the input data are deterministic and the model itself is completely deterministic, we do not in general talk about simulation. What actually we do is a numerical analysis of the system. It may still be very complex mathematical model, so we may put in deterministic stimuli and observe the output results. If the system model is deterministic and we input stochastic input, we talk about the Monte Carlo computation. It's still a numerical analysis that we do of there's nothing random about the or stochastic about the model itself. It's just that a way how to efficiently compute certain results in this deterministic model. And we'll come back and give a few examples of this. And the lower right-hand side is the core of our study here in this course, and that's what we call stochastic simulation. And that is when we have stochastic components in our model, and also we drive the model with the stochastic or statistical stimuli or random stimuli. And that the lower right-hand corner will be the focus of this course. So let's discuss a few of the problems that we face in stochastic simulation, and which we will tackle in this course. But before we start, let's mention a few words about the things that we will not tackle in the course, and that is the actual implementation of the simulation. What kind of software, what kind of programming language, what kind of programming environment you will use is not part of this course. We expect that every student is capable of handling MATLAB or Java or any programming languages of a choice, but this will not really be part of the course. We will focus on experimental design and the statistical problems in the simulation techniques. So what are the problems that we are facing in the stochastic simulation? Well, since these are experiments, even though run in a computer, they still have the same problems as any empirical science. We cannot prove anything by experiments. We can only falsify statements, or we can strengthen a model, but we can never prove anything by experiments. Not in the strict logical sense. We have validity problems. Are the models for the systems and the stimuli that we use, are they really relevant? Are they accurate? Do they describe reality in an appropriate way? And this is the modeling problem. And on top of that, we have statistical problems. Are the measurement results, the performance result that will be derived from our simulations, are they accurate? Are they representative? Remember that we now have both random, in stochastic simulation, we have both random models and random stimuli. So the output will be random numbers or random variables, and so the question is how accurate are these results? And we will also focus on how can we design simulation experiments to improve this accuracy. Here are some examples of typical simulation experiments, and also examples of what questions can we pose and what type of answers can we expect to get from simulations. What is the expected message delay in network A is a typical question you can answer. And that is, you can call a parameter estimation problem. Is QA moving faster than QB? Yeah, that is what you call a hypothesis testing problem. And this is also something that we can attack using simulations. And solve this integral. That's what you call a Monte Carlo integration. This is an example of Monte Carlo computation where we have a completely deterministic. The integral has a value. We don't know it, but it has a fixed value. But we use stochastic data to evaluate this integral to get an approximation of the integral. So let's look at the first problem. What is the expected message delay? How would we do that? Well, we create a system model of our network, and we enter n messages into the network, and then we record the delays that these messages occur. And these will be random numbers, and we model them as a stationary ergodic random process, and then we have use the mean value as an estimator of the expectation. And the performance is then the variance of this estimator. As you can see, the stochastic observations, they will fluctuate around this mean value, and the more observations we can get, typically the variance will decrease, and we get a more and more accurate estimate of the delay. The other example is QA moving faster than QB? Or to be one way of designing this experiment is to ask, is the expected delay of QA lower than the expected delay in QB? And the experiment would be to look at the two queues, and we feed A and B with identical random inputs. That the inputs are the arrival patterns of the customers, of end customers, and then we observe the delays for the two queues, and we get data like in the plot on the right hand side, where the squares and the black dots represent the delays for QA and QB, and we could estimate the average delays and compare them, and if the difference between the expected delays is large, we can probably decide that one of the queues is moving faster than the other. If the difference is small, we usually cannot make any statistically safe statement about the hypothesis. So let's have a look how the hypothesis testing is done. Again, we model the two sequences of delays as stationary ergodic random processes, and the hypothesis H0 is that the expected delay in QA is less than expected delay in QB. We design a test metric E tilde, that is in this case the average of the differences between the delays and the different observations. And then we compare this test statistics with the threshold, and if it's lower than a certain threshold, we accept H0, and if it's above the threshold, we discard H0. The performance is measured as in terms of the miss probability, and that is the probability that we reject H0 even though it's true, or the false alarm probability that we accept the hypothesis even though it's false. And finally, let's have a look at the numerical integration example. The problem here is to solve this integral between 0 to 1 of e to the minus x squared over 2, for which no closed form exists. And the way we do it is that we generate n pairs of identical distributed random variables with uniform distribution of 0, 1, and x and y, and they will sort of scatter the unit square 1, 1. And simply what we want to do is want to count how many of these random pairs fall below the curve e to the minus x squared over 2. And the way we do it is that we define zi, the observation zi, as an indicator variable, and it's 1 if it's if y I is below the curve, and 0 otherwise. So it's if the x y pair is in the shaded area, and 0 if it's in the white area. And the average z bar will then be our estimator of the integral, and that is the proportion of the area that lies below the curve, which is the shaded area. And the performance here is the variance of z star, and as we will see later, the variance can be made arbitrarily small by increasing the number of simulations. And this brings us to quiz 2 on stochastic simulation. Again, pause and figure out the answers, and I'll be right back. And the answers are B. Monte Carlo computation is a numerical method for evaluating complex mathematical expressions. And the key problem with simulation experiments is they cannot prove any theory to be correct. And this brings us to quiz number 3, which is actually a small problem. We can apply the methods that we discussed before. Here we assume that we can generate a sequence of independent pairs of random variables x and y with a uniform or rectangular distribution of the interval 0, 1. And we would like you to devise a simple simulation experiment that can be used to compute an approximation of pi. So again, pause here and use a piece of pen and paper and try to solve the problem before going to the solution on the next slide. And here's one example. Again, as in the previous numerical integration problem, we use the fact that the area of a circle with the unit radius is pi. So a quarter circle segment like this has the area pi over 4. So again, we use the uniform pairs x and y that will sprinkle the unit square, and then we'll count how many of them fall below the circle circumference in the shaded area. So we form zi as 1 if x squared plus y squared is less than 1. That's the point is in the shaded area, or 0 otherwise. And we calculate z bar as 4 times the average of z, which then will be, since the average of the z's will be pi over 4, then the average of z bar will be pi. And this concludes the first lecture.